All right, good morning, everybody. Welcome to our webinar this morning on ProtectoWire's linear heat protection. Obviously, this is a technology that's been around the industry for quite a while, but we're seeing it used more and more often. So we've invited ProtectoWire to come and do this webinar today. We're very glad to have him. Gary Paul is going to be the one presenting this morning. If you guys have any questions, I've got all of your microphones are muted. So if you guys have questions, please type them in the chat box. You'll find that up in the top right-hand corner. Type them in the chat box, and we will take breaks a couple of times throughout the presentation to make sure those questions get answered. So with no further ado, I'm going to go ahead and hand it over to Gary. And Gary, you are muted, sir.
I'm going to figure out this program before this is all over, that's for sure. All right, I apologize for that, but I just wanted to say thank you for having us on. Always a great opportunity to be able to talk about the technology, even after 85 years in business. It's amazing the number of times I meet new people in the field that aren't aware of what the product is or how it's been utilized, things of that nature. So again, thank you. So we're just going to go and kick right into this. So hopefully today, what I wanted to do is talk a little bit about the technology, the different products that we offer, the different forms it comes in, different operation techniques and things of that nature. But start off, as it was introduced, my name is Gary Paul. I'm the regional sales manager here at ProtectoWire. My territory covers the US and Canada, where I manage all our distribution partners. And I also get involved in a lot of these education seminars and webinars to kind of further the education and understanding what linear heat detection is, how it falls within the special hazards industry, and things of that nature. Inside, part of our team, Brenton Harris is our VP of Sales and Marketing. Vernon Gross is our Business Development Manager. And then inside, Amy McCarthy is our Inside Technical Sales, who will work with most of our partners, engineers, end users on the different products, applications that they're working on, and how to best apply the technology. So linear heat detection was invented and patented in 1938 by a gentleman by the name of Gerald Holmes. Back in 1938, it was rumored that there were certain occasions where there was a need for some sort of a heat detector to be able to capture and identify when either a fire was happening or a hotspot. Gerald Holmes was a Columbia grad and an inventor, and spent some time here. I mean, we're literally located, our new office here is about 200 yards from where he originally invented linear heat detection in his barn. And that barn, served as our manufacturing center of operations for the next 70 some odd years. It's only been the last 12 or so years that we've been in this new facility, and we're already starting to bust at the seams. But as you can see, the patent back in 1938 was essentially two pieces of music wire. The separator between those conductors, the dielectric per se, was beeswax. He was looking for something that would react to heat and melt away to expose those conductors. In its operation, linear heat detection is classified as a digital contact device. So that means it has two states of operation, either on or off. So having it in that open, it's a normally open contact device. Once those polymers short, that's where we create the short and the alarm condition. So, and as the slide says, our focus has not really changed in 85 years. We've advanced and expanded the product line from what it was back in the 1930s, obviously with the advance of material sciences, things of that nature, manufacturing operations. We've been able to expand and broaden the scope of the product line to address not only different capabilities when it's being tied into other people's control equipment, but also taking a look at the environmental concerns that are out there. At one point in time, I mean, it was cloth braid and beeswax. Now we're looking at different types of polymers depending on where the product's going to be installed. So we have our PVC jacket, we have a XCR, which is a fluoropolymer. We have an XLT, which is our acronym for extreme low temperature. And I'm just going to, quick side note, I'm going to apologize in advance. I've got some construction going on here at the factory today, and they are literally right outside my window. So if the noises start to creep in, please, forgive me. I can certainly repeat myself if anything gets drowned out in the process. And then with the advent of the different styles of linear heat detection, at one point in time, we still offer our own brand of conventional control equipment, releasing panels and things of that nature. But now with the advent of addressable systems being so ubiquitous within the marketplace, conventional is kind of a technology that's not really leaned towards, other than to know that, these conventional technologies are workhorses. We've seen some of these panels survive, with good maintenance and, making sure it's installed in the right place for 10, 20, 30 years. In fact, I'm working with a company right now that has a panel that's been installed since 1969 and it's still in operation. So just a testament to what the solid state relays and things of that nature can do over time, and, the capabilities it gives you for longevity. And then there's fiber optic linear heat detection, which is kind of a detour from what your standard linear heat detection, where, conventional linear heat, our PHSC, our digital series, and our CTI are passive devices. So we're waiting for those polymers to melt, short, to trigger an alarm condition, whereas fiber optic is more of an active temperature monitoring system that we can program the head-end controller. For lack of a better word, it's nothing more than a glorified interface module to be able to react at specific set points, rate of rise. We'll get into that a little bit as well. So as I was mentioning, linear heat detection is just a unique cable. As far as its manufacturing and things of that nature, it looks and would classify as a wire. It's a 4 millimeter diameter construction, 2 conductors. We use a wrap. We'll get into that. But as I mentioned before, too, is that it is categorized as a digital device. So when I say digital, it means binary. We're looking at 2 modes of operation. It's either on or it's off. So once that detector shorts, that's what triggers our alarm condition, and then the sequence of operations programmed into the panel take over. In addition to that, we've been UL and FM approved since the 1940s. So we were one of the original companies participating in the local NFPA movement as far as getting listings and things of that nature. So the best way to describe a linear heat detection, it's just like a continuous chain of spot heat detectors. So that means anywhere along its length, wherever it's installed, those 2 conductors are in a position to react to an overheat condition. And once that fixed temperature profile is achieved, it shorts out, creating that alarm condition. The product is very simple. As I said, it's a 4 millimeter diameter wire. It's a normally open contact switch. As far as its capabilities, because of its profile, because of its size and its style, it's very suitable for a wide variety of different applications. So not only are we listed along similar devices as, say, a spot heat detector for open area listed spacing, the size and the shape and the style of the product lends itself very well to being in close proximity to the hazard that we're trying to protect. So obviously within the special hazards industry, a device like this is not so much focused on life safety as it is looking at asset protection. So the basic conditions of our standard digital linear heat detection, and within our family of products, this is known as our PHSC series and our PLR. So PHSC is our acronym for ProtectoWire Heat Sensitive Cable. and PLR is ProtectoWire Low Resistance. So we'll get into the reasons for the different distinguishing characters of that. But in essence, what we have are three primary conditions for the linear heat detection. Normal, clean, and green means that we're regulating current flow through the length of the detector. In a Class B configuration where the end-of-line resistor is located out in the field, we're monitoring and regulating that current flow with that resistor. We can determine when we have it open. This is, when one of the conductors has been cut, unseated from one of the terminal blocks, and end-of-line resistors become unseated. That means we've stopped current flow going through the line, and the monitor module will recognize that as a flow stop and trigger it as a trouble. And then obviously we have our alarm condition. This is when those two heat-sensitive polymers melt, exposing those conductors, creating that short, increasing the voltage flow through the line, and triggering an alarm sequence on the actual panel. So as I was mentioning, back in the day, there was only one style of linear heat detection. And as we advanced over the years, we wanted to start creating additional product offerings to accommodate different scenarios and different applications. So PHSC, as I mentioned, is kind of the product line that everybody recognizes and they associate the most with our name. So a lot of times when folks are out in the field and they see linear heat detection, doesn't matter which manufacturer it was, they're going to look at it and say, well, that's the ProtectoWire. So PHSC, two steel core conductors, heat-sensitive polymers, and then the protective jacket. PLR, as I mentioned before, is our low resistance. So with each one of these, not only is it a normally open contact device, but it's also classified as a resistive contact device. So that means for every foot of detector that you pull onto your IDC, you're drawing that much resistance off that module's ability to support the detector. So obviously, depending on what that module's ability to support loop resistance is, will determine how many linear feet of detector you can support off your module. And that's the nice thing about the PHSC and the PLR is that we don't need proprietary control equipment to be able to support the detector. All we need to know is what module is it going on to, what is that module's ability to support loop resistance, and then we can do some quick math and say, okay, based on the modules that you have spec for this job, you can expect to be able to support X number of feet off of this module. Now with the PHSC, that resistance is at 0.185 ohms per foot. The PLR, what we're doing is we're adding a copper coating on that to reduce that resistance value. So the lower the resistance, the more detector we can push off of that same module. And we'll get into that as well. CTI was introduced about 10 or 15 years ago to answer the issue of false alarms. So with the standard digital linear heat detection, it's not a very intelligent device. Cannot tell you the difference between a heat event and somebody smashing it with a hammer or a forklift. So with CTI, we're able to change the primary conductors. Now when this goes into a short, we have a required interface module that then converts it to what I like to glorify as just a digital thermometer. We program in the set points that we're looking to achieve, and as long as it stays below that set point, it stays in a fault condition, tells you where the pinch is. You can cut it out, repair it, but it's still active. And then fiber optic, as I was mentioned, this is kind of a left turn as far as linear heat detection is concerned because it's not passive. It's more of an active temperature monitoring. So it brings about its ability to be applied in a wide variety of applications. And then the information that we're drawing off the facility just by being able to monitor temperature profiles lends itself to building management systems for different applications like tunnels and aircraft hangars and things of that nature. Now, along with the different conductors that kind of, identify and give the detector its unique capabilities, the outer jacket is there for environmental concerns only. It has absolutely nothing to do or no impact on the actual activation temperature that you're looking to achieve. These different jackets over the years, PVC was the predominant jacket option for a number of years, but it has its limitations. PVC is not very good when it comes to heavy industrial and caustic environments. It doesn't hold up very well in outdoor applications. UV rays will eat away at the other jackets and prove them to become brittle over time, and then you're dealing with a lot of false alarms. XCR was invented and brought about to address some of those environmental concerns. So XCR is a fluoropolymer, for lack of a better word, a Teflon style jacket that is impervious to a lot of different chemicals, oils, solvents, things of that nature. UV stabilized, so you can stick this out in the Arizona sun directly on rooftop or transformer application, and you don't have to worry about the jacket degrading over time. XLT was brought about 5 to 8 years ago, and that's our acronym for extreme low temperature. So this is our lowest temperature rated device. It only comes in one activation temperature at 135 degrees Fahrenheit, but the jacket itself is rated to -60, whereas most of our other jackets are only rated to -40 degrees Fahrenheit. And then PLR, it only comes in one jacket option. So if you order the PLR, it's a low resistance conductor, and it's a thermoplastic rubber jacket. So similar to the XCR, it's going to be impervious to a lot of the oils and solvents and chemicals present in a lot of industrial applications. But it also only has 2 activation temperatures available at this time, 155 degrees and 190 degrees Fahrenheit. And this,
Gary,
yes.
Real quick, but before we move on, I did want to throw out there, just in case anybody's wondering, Potter input circuits, whether they're on a module or one of the I/O circuits on control panels, can take 100 ohms.
Yep.
So we were talking about the load. 100 ohms is going to be our max. And we did have Tim Moore ask, can this be used in an elevator shaft? So you've shown several different models here. We may want to discuss that application. I don't know if it fits in right now, but I did want to put that.
To be honest with you, I have actually a slide that I put up there on the 4410 where you have 100 ohms IDC, but it also has a disclaimer saying except for linear heat detection where it's 700 ohms. So I kind of threw that up there, and I thought I'd throw it out to at least you and possibly the Potter group to sit there and confirm what that actually is, and maybe you just answered that question.
That is correct. Linear heat detection, we are allowed 700 ohms. Just regular IDC input is going to be 100 ohms, but we are allowed 700 on LHD. So I apologize. Thank you for the correction on that.
No problem. No, I did a little research this morning. I knew that there was a significant difference, and there was a lot of capabilities out of the panel. So I wanted to make sure I highlighted that here for this session. And then with our linear heat detectors, as I mentioned, these are all fixed temperature devices. So we offer them in very specific activation temperatures, and then each one of those activation temperatures is color-coded to correlate with that number, just so we can quickly identify what we have installed, things of that nature. So red is always going to be 155 degrees, white is always going to be 190, and so on. And currently, we run the gamut from 135 degrees activation, and our highest rating at the moment is 500 degrees Fahrenheit for specialty furnace applications and things of that nature. And on the CTI detector, same thing, same color coding, same temperature profiles, except for this one. I don't have it listed here, but we do have the 135 available for the CTI, and we go up as high as 356 degrees Fahrenheit. So the basic construction, as you can see here, I mean, looks just like a piece of fire alarm wire. The big difference is the 2 primary conductors are steel, spring steel conductors that are zinc coated. because they are steel, we want to make sure that we don't have any rust or anything like that, because just like steel, these conductors could have the tendency to rust over time, depending on the atmosphere and the environment it's in. Adding that zinc coating on there just protects the conductors and the steel from having impact. Once we get the conductors ordered and everything else, we apply the heat sensitive polymer. So each one of these is specifically designed for their melt index and their ability to wick away at that fixed temperature point that we want. And I always describe the polymers that we use on this as kind of like a candle wax. So in the morning, you see a tapered candle in a sunroom. If it's cool, it's standing straight up. But as the heat, impacts that room, you're going to see that tapered candle wilt and, fall over. Same exact principle that we're trying to apply to linear heat detection is that these polymers, as the temperature rises within the area that it's protecting, those polymers are going to begin to soften and melt away to expose those conductors so that once we hit that activation temperature, we're going to short out and send that signal back to the panel. Once we get through the extrusion process on the primary conductors, we then induce a twist to it. And typically what we're looking at is a few twists per foot just to get that spring tension between the two conductors so that the conductors are as close as they can possibly be together so that when they do melt and those conductors are exposed, we're in perfect position to respond as quickly as possible. And then once we get through that, we apply a Mylar wrap to hold the whole construction together. So those conductors have no place else to go. There's no loose over jacketing on just the outer conductors. So this is all very nicely and tightly wound together so that it has absolutely no place to go. And then also adding that twist into it gives it a little bit more flexibility. As I mentioned, this is steel spring. Think of it as music wire. So it has an incredible memory. I'm going to caution anybody that is actually working out in the field on one of these. If you haven't had the experience of trying to cut linear heat detection with a standard pair of wire cutters, my first recommendation is don't. Get yourself a set of heavy-duty, hardened wire cutters. It's the only thing that's going to cut through these steel cutters. Standard wire cutters are just going to get damaged, and you'll never be able to use them again. Once we get that done, then we add our outer jacket, and this is all based on the activation temperature, the color of the jacket, and then whatever form we're going to offer it in, whether it be our standard PVC, our fluoropolymer, or our rubber jacketing. After the extrusion, one of the last processes is to print and identify the detector. So on this, we have our brand name on there, our product identification, full part number. We carry both our FM and UL listings, so it's clearly identified. You're going to have your activation temperature on there. You're going to know what your jacket type is. In addition to that, we also include lot code traceability on every lot that we manufacture. So once we have if there's ever an issue with or a question of the quality of the detector in the field, or you're having problems, we can go back to the manufacturing records for that particular lot and call up all the materials that we use, certificate of compliance for each one of those primary materials, as well as all the test measures that were taken, not only from the beginning all the way to the final and test, where we actually put pieces of the detector in an oven, set it to its activation, and then measure and record its how close to the activation temperature it goes off. And right now, standard deviation on any one of these detectors is usually within 1 to 2 degrees of its activation temperature. And then I always throw in here that all important, do not paint. So once upon a time, back in the way days, it was recommended not to paint the detector more than twice. Paint doesn't really impact the detector's ability to react to an overheat condition. What's more important is that once you paint the detector, you've obliterated all the markings on the cable, making it unidentifiable. So you don't know if it's a piece of fire alarm cable, you don't know if it's a piece of communication cable. and you don't know whether or not it's a heat-sensitive device that's there to protect the building. So our recommendation now is that, to maintain our listings, once you paint it, you void all listings. So right on the jacket, we're going to put right on there, do not paint. And if it gets painted, the HJs are going to call you out on it. So as I was talking about the different conductors that we use in the construction of the various detectors that we manufacture, the steel spring conductors has an inherent resistance value. And in this case, it's 0.185 ohms per foot or 5.4 feet per ohm. And then as we add the copper coating, we reduce that resistance value by almost 2/3. So we go from 0.185 ohms per foot down to 0.058 ohms per foot. So as you can see, it's a difference of 5.4 feet per ohm all the way up to 17.2. So just by adding that layer of copper onto the conductors, we've almost or more than tripled the amount of detector that you can support off a standard IDC. Oh, thought I had it here. There it is. These are in kind of a reverse order. I'll go to this slide first. This is what I was talking about earlier. So off a standard monitor module. So as I was mentioning, we don't need necessarily proprietary control equipment to support linear heat, depending on the equipment that you're using and the amount of detector that you need to cover the specific zone that you're going out into. So I took two examples here. One was just a typical monitor module, addressable module that has 100 ohm loop resistance capability off the IDC. So based on the resistance values of the various detectors, so PHSC off 100 ohm IDC, we're looking at about 500 feet that you can support off that module. I think the exact number is 540 based on that 5.4 feet per ohm. With the PLR series, just adding that copper conductor, we can triple that output to be able to support over 1,600 feet of linear heat detection. CTI and fiber optic, you're going to notice, are static at 4,000 and 32,000 feet, simply because those two technologies do require a proprietary interface module, and that is the capability of the equipment that we provide. So now taking into example the Potter 4410 module, as we discussed, 700 ohms on the IDC there. So I did some quick math this morning, and looking at PHSC, you can support up to 3,700 feet. So that's a little over a half mile worth of detector. Adding the copper onto that boosts the output to almost just around 12,000 linear feet. And that's an awful lot of detector. I always say, if you're going to put this much detector off a single IDC, your best bet is to have some sort of an alarm point meter built into it so that you can easily identify where in the field, because linear heat at the end of the day is not addressable as far as where along its linear path it's had a compromise. Instead, what we can tell you is, based on the resistance and where that pinch is, it's going to give you a different reading. Some quick math, you can identify out in linear feet whereabouts that pinch is occurring, but now you've got to go out, walk the line, find where that spot is, and then make your repairs there. And then again, CTI and fiber optic, those require special interface modules, so those numbers are always going to be static at 4,000 and 32,000 feet. And just to address some of these larger applications where you don't want to order one of our panels, we do offer interface modules. So for our standard PHSC series, using our PIM 530 interface module, now we can monitor up to 6,500 linear feet of this particular detector. The module comes equipped with Class A and Class B configuration. So Class A being that we're doing a complete loop, exiting our module, running through our facility, and then returning back to the module and monitoring the detector in two directions. Class B, you're just ending out in the field with the end-of-line resistor, and that's all one direction. It does have integrated alarm point meter, Form C contacts to be able to tie back to anybody's panel. 420 milliamp outputs, not used so much these days, but it is a feature that is built into the into the module. Optional 4x, NEMA 4x enclosure. And then we have the ability to daisy chain these modules through Modbus. We have a 64 event history, first in, first out. And the module does require between 12 and 24 volts to be able to power it up. So off a standard panel, you might be able to power one, maybe two of these modules off the auxiliary power, but recommended more often than not to bring in your own separate power supply, like an Altronic or something along those lines, just to make sure you have continuous power to the unit. As I was mentioning, CTI is kind of a left turn or an advancement within the standard digital linear heat detection world, in that, as PHSE and PLR, as I was mentioning, aren't very intelligent. They can't tell the difference between a heat event and physical damage, mechanical damage. CTI was brought along to provide that short circuit discrimination. So when this detector shorts out, the interface module turns into a glorified thermometer. And we do this by the two primary conductors. So as opposed to our standard steel or copper-coated steel, we're using a combination of two dissimilar metals, copper being one and constantan being the other. So in the thermocouple world, this is what's classified as a type T thermocouple. And type T thermocouples are used a lot in your temperature monitoring, temperature sensing applications. So classic example of this would be your digital thermometer. One that you might have in your kitchen window. You fish a little wire outside, and you can read the temperature profile outside without having to go outside. So on a cold day, it's going to register those ambient conditions outside your window. And that's exactly the same concept we have here, except we're leaving the conductors open. So it's still a normally open contact device. Its operation is the same. The heat-sensitive polymers that we use to provide that activation temperature and profile is the same. The construction is all the same. It's just those two primary conductors that have changed. And thermocouples are a device consisting, as I mentioned, of those two dissimilar metals. Within the interface module and the pinch out in the field, we have what is considered a hot junction and a cold junction. And then through algorithms, we just compare the two through a voltmeter. So it was discovered years ago that when the two conductors actually touch each other, they emit an electrical discharge in the microvolt range. And then as temperatures increase and decrease, that voltage will increase and decrease in direct correlation with the ambient conditions outside. So now through the algorithms, we can tell you within a degree or two what the physical temperatures are in your field compared to the activation temperature. So if you're in a cold storage environment, in-rack detection, and you have constant, pinches and air pressure being lost or water being flooded into the pipes, we all know what that problem, results in. It's a costly six-figure reset to be able to thaw out the pipes. If we release water, reset the air pressure within the pipes as well. So having this false alarm discrimination saves the ability not to react, because there's a lot of manual operation goes into some of these facilities. We're seeing more and more of the automatic storage retrieval systems coming online, but there's still a number of manually operated warehouses out there that would benefit from this type of discrimination. So, as I mentioned, it's the same type of operation. It's still a passive device waiting for that heat event to occur. We can still determine when we have an open, meaning that we've stopped the current flow going through the line of detection. We can determine when there's a shortfall, except when we get a shortfall here, that is step one. As opposed to our PHSE and PLR, that would be an automatic alarm condition. In this case, a short would then trigger back to the module. The module is going to be programmed for your fixed temperature. So here I have depicted a 155 activation. If the module comes back with an ambient temperature of 75 degrees Fahrenheit, that doesn't meet the activation temperature. So therefore, it stays in a shortfall condition. Alarm point meter is going to identify where that is out in its linear path. You can go out, cut out that section that's been damaged, splice in a new section of detector, reset your module, and it's good to go. The nice thing about this, in addition to that, is that now that we've got a pinch and a short out in the field, in a Class B configuration, the detector is still active and able to react to an overheat condition along the length all the way up to and including the spot of that fault. In a Class B, anything from that spot of the fault out to your end of line resistor, that becomes your dead zone. In a Class A configuration, because we're monitoring in two directions, we don't actually lose any detection capabilities throughout it, unless there's two pinches or two shorts within the other line. Then that area in between those two faults would become your dead zone. But we're still monitoring in two directions and still identifying whether or not we have an overheat condition. And this is a good layout of what a Class A or a Class B layout would look like. So similar to our PIM 530, the CTM 530 is the brains for the CTI detection system. We can support up to 4,000 linear feet, but there's an asterisk with that. Because we've changed these two primary conductors to a type T thermocouple, in order to get the proper reading to determine what that temperature profile is in the field, everything that comes in contact with those two conductors has to maintain that type T thermocouple principle. So that means we have to maintain copper and constantan in all the devices that we use when connecting. That includes feed cable. So you can't use copper feed cable with this to run out to your zone to transition to your detection. So you have to have type T rated feed cable. Terminal blocks that are used inside the zone boxes have to be type T rated. Splice connectors are type T rated. So that means each one of these has that copper on the positive, constantan on the negative, and that will maintain the current flow and gives us the ability to distinguish that microvolt discharge I was mentioning to determine and correlate that into a temperature profile. Once we start adding in other types of materials like copper feed cable, you start skewing that information and may give you false positives and or false negatives. And as I mentioned, the modules come standalone. We also offer it with a NEMA 4X enclosure. And these modules, as I said, Form C contact, so that means this could be tied right back to anybody else's control equipment, whether it be a Potter panel or some other manufacturer. Just your standard IDC would be able to support this and register the alarm conditions off the module. Now, as I was mentioned, the fiber optic system is a very unique detection system where, as opposed to being a passive device, this is an active temperature monitoring system. So the most recent version of the fiber optic system is the N45. We're supported through AP Sensing. We use their control equipment, and for years we've been building them into our own cabinets. The fiber cable is a 50 micron single mode or multi-mode fiber optic cable that's available either as a metal-free or a fully reinforced style cable assembly. And the controller is an optical distributed temperature sensing device. So what we're doing is we're sending beams of light down the length of the fiber, measuring the backscattered light within a very specific frequency band to determine temperature profile. Again, I mean, just like all linear heat, it gets installed in the same exact manner. It is 4 millimeter diameter, just like everything else. So that means it's compatible with all the different support accessories that we offer, which, you know, the support accessories we provide are specifically chosen and or designed and manufactured to be able to support that 4 millimeter diameter without putting undue pressure around those polymers. With our digital devices, putting too much pressure around those polymers could have an impact on its capabilities further down the road. You may get intermittent faults, false alarms, things of that nature. So our supports are designed to hold the detector in place without imparting any unnecessary force around the conductors. The other nice unique aspect of the fiber optic is because we're dealing with light waves. Depending on the model that you go with, we can support up to 16 kilometers in a particular channel configuration. So each one of the controllers comes with the option of either a 1-channel, 2-channel, or a 4-channel configuration. And what I mean by channels is that that's the amount of detector it can support, fiber optic detector. Either one fiber going out in one direction, 2 going out in 2 different directions, or 4 going out in 4 different directions. And each one of those can support up to 16 kilometers, which is in roughly about 52,000 feet of detector, almost 10 miles. The sensor cable and the control equipment have a robust life expectancy. Right now, mean time between failure is estimated at about 30 years. The other aspect of it is that it's immune to electromagnetic interference. So having light waves out into, going out into a field, you don't have to worry about any EMI. So this is the basic controller where we have our power LEDs, we have our measuring capabilities, and all the information is going to be programmed and displayed through here. Programming of the actual unit is done through software, a web-based software system where you can segment the cable up to 2,000 individual partitions, or for lack of a better word, zones. So you can create zones where you turn on detection. You can turn on detection. You can set it for one fixed temperature. You can set it for rate of rise. You can set it for fixed temperature and rate of rise. And then all the while it's monitoring the environment it's in, it also has a memory in there that knows what the average temperature is, at any given point in the day. So you can actually program it to alert you when those norms are violated, whether the temperature drops drastically for whatever reason, or suddenly there's a hotspot that's developing over a period of time that you want to be able to investigate. The 2 different fibers, as I was mentioned, the fully reinforced is a steel wire armor. So this is what would be considered like almost like a rodent-proof type of jacketing to protect the fiber outdoors, make sure nothing's chewing through it or anything like that. It also gives it some additional strength in certain applications. And then we have our metal-free, which is your typical fiber optic cable. The fibers themselves are protected with an aramid yarn. And each one of the constructions, each one of the cables comes with 2 core fibers in it. But at any given time, depending on your configuration, more often than not, you're only going to be using one of these fibers. And again, I mean, anybody that's dealt with fiber optic cable in the past, the 50 micron, you're talking about the width of your hair. So as I was mentioning, we're pulsing a beam of light, just like any other fiber optic system. Same with communication lines and things of that nature. And we're measuring the backscattered light. In this case, the backscattered light we're looking at is considered and called the Raman backscattered light effect. So it was discovered back in the 30s that light waves have different paths. We all know about the different colors and things of that nature, but with temperature monitoring systems, there are 2 very specific. It's referred to as Stokes and anti-Stokes, one being temperature dependent, the other being temperature independent. And then being able to compare those 2 specific light frequencies, we can correlate and go through algorithms to determine the specific temperature within a degree or 2 as to what's happening within the section of the fiber cable. Now, obviously, when you're considering the fact that you can support up to 52,000 feet, times 4, so that's over 200,000 feet off of one controller. We're not going to sit here and tell you what the temperature is every millimeter or every inch down the length of this fiber. The computational aspects of doing something like that would be overtaxing and would delay the ability of the system to be able to respond to an overheat condition in a predetermined period of time. Typically, we'll want to see an activation within 30 seconds of the activation temperature being achieved. So with a system like this, having that number of calculations, just delays that ability. So now we talk about spatial resolution, where the fiber cable and the controller is going to take a snapshot of that temperature profile and what that backscattered light is giving us at specific intervals up and down the length of the fiber. The longer the fiber, the further out that this detection points are going to be calculated at. So in a 10 kilometer, you're looking at typically about every 8 meters is going to be your spatial resolution. In a 1 kilometer, we can get that down to probably every meter or two. So you're getting a little bit tighter configuration. So what's happening is that the snapshot is being taken, and then every third line, they're averaging those 3 temperatures together to give you a profile. And it just continues to do that up and down the length of the fiber. One key element to point out when it comes to fiber optic cable, it can be spliced. So if there is a damage within somewhere in the field, or as you're installing, you need to add more detection to the system, and you have the headroom off the interface module to support it, you can't just use butt splices on this and cleave it 90 degrees. Fusion splice is the only recommended method of splicing these wires together, because we want to minimize the line loss, that light wave frequency coming back. With a butt splice, you have a certain dB loss that exacerbates the ability to identify those temperature profiles. Fusion splicing is the effect of taking the cable, the fiber cable itself, and cleaving those fibers at an 8-degree angle, and then fusing those two halves together. Now you've broadened the surface area of those fiber cables to allow more light to go through and minimize that loss. And then the 3 primary elements that you can use the information coming off those temperature profiles is you can now program into your units and identify your zones and set your fixed temperature profiles. You can also program in a defined rate of rise or rate of change, and then deviation from zone, where we know what the average temperature is at any particular time. And now we're starting to see anomalies that we can start alerting control operators, personnel within the field, within the system, to what's going on. And as I mentioned, you can program each one of these fiber cables into up to 2,000 unique alarm conditions in zone configurations, which is pretty incredible. And then on top of that, we can trigger up to 98 relay contacts. So testing of linear heat detection for fixed temperature, rate of rise compensated, restorable type detectors, a heat test is required, should be performed. These are not going to be anything that needs to be fixed, but where typical ProtectoWire linear heat detection is a non-restorable heat detector, they recommend not performing any heat tests. Some AHJs still like to see that out in the field, but all that needs to be done with a non-restorable type of linear heat detection like ProtectoWire is you short it out at your endpoint, whatever the end of your zone is, and show that you can record and register an alarm condition or a fault condition at the panel, something that changes that condition, and know that the detector is in good shape and it's ready to operate. The nice thing about the CTI detector is that because of the terminal blocks that we use, they have an integrated test jack in it that you can plug in a test probe, a heat probe, short out the detector. It's going to register back at the module where that short is, what the ambient temperature is, and typically it's going to be in a fault condition. Now with that 6-inch probe off the jack, you can actually hit that with a heat gun and simulate a heat test, show the module's ability to go into alarm, and then trigger an alarm condition on the panel without actually damaging the detector. So it's a nice feature to know about. And then as far as listed spacing, just like other types of heat detectors, spot heat detectors in particular is where we're closely compared to. Per UL and FM, so for FM, it's typically between 25 and 30 feet. And then UL, we're 50 feet across the board. And that's all based off of a 10-foot smooth ceiling. And then as the ceiling height goes up, NFPA 72 has special requirements for recalculating and derating that listed spacing up to 34 feet. Once you get beyond 34 feet, it becomes 40% of the ceiling height is your new listed spacing as that ceiling height goes up. And then the different types of application, as I was mentioning, because it's such a unique construction, there's a wide range of areas where this can be applied. We see it a lot in cable trays, just being able to monitor for overheat conditions with some of these high voltage cables. Having a nice S pattern going over the top of the cable tray puts it in close proximity to the areas that you're going to most often see some overheat or a fire condition. So as that fire travels, it's in a good position to be able to capture that. And even as the cable tray, traverses from horizontal to vertical, you can continue and maintain that close proximity to the cables to be able to detect that fire. Now, linear heat detection per se doesn't have a vertical rating as far as any kind of listings. All the listings as far as open area is based on horizontal installations. But, vertical detection, that's where it's going to become proximity. It's just a matter of how close you can get and want to be to the area you want to protect to make sure that it's in the best position to be able to react. A lot of conveyors use linear heat detection, and in this case, it's the bearings that are typically the first things that seize up and create an overheat condition. So now in a classified hazard where you have combustible particles in the air, dust, things of that nature, an overheat condition can trigger a chain of events as far as fires and things of that nature very quickly. So having the linear heat detection in a close proximity to those bearings to sense when those areas get overheated gives us the opportunity to hit an e-stop and just shut down the conveyor, keep it from moving any more material. In the cases of hooded conveyors that have deluge systems built into it, we can run the detector right along the deluge pipe and then be able to react, release air, and then trigger a suppression system. Transformers are another great application that we see a lot. Typically, we see it up and around the deluge valves going around. And in this case, once the transformers start to go, it's just protecting that area and making sure that the fire doesn't spread to other transformers. In some applications, we've seen some areas where they've actually applied the detector directly to the transformer so they can capture that overheat condition even earlier and be able to respond. So now, taking into consideration that we're running current through these cables, we don't want to make a complete loop around a transformer. Now you're just getting into EMI, RFI issues that could have other issues with the system. So as you can see here, you're not making a complete loop around the entire transformer. Rather, you're just coming as close as you can, and then traversing back around and back to your panel. Refrigerated and warehouse storage facilities is probably one of the most common applications, common areas that we see linear heat being used. In particular, FM 829 for cold storage and a PA 13 are the two primary drivers for requirements for detection within these storage facilities and these storage racks. So if NFPA 13 calls for in-rack sprinklers, with the sprinklers, it needs to have a level of detection, especially in a cold environment. You don't want to have water in those areas because it's just going to freeze. Linear heat detection has been the predominant detection device in these areas simply because of its profile and its ability to span those lengths of the racks and be in a good position to be able to respond to a overheat condition wherever those fires take place. The other area that we're starting to see a lot of buzz and a lot of talk about is solar panels. So here in the United States, for years it was never really classified as a fire. It was always classified under other. Now they're starting to make a more concerted effort to identify fires on top of these rooftop solar facilities. So a lot of major distribution centers are starting to utilize their large footprints on top of their roofs and installing solar panels to help offset some of their energy costs. Well, with that, we're starting to see fires. And it's not so much that the solar panels themselves are catching on fire. They are, but they're not the cause of the fire. Usually it's something to do within the electrical system, either a bad connection, bad wiring, or animals, nesting in and underneath some of these solar panels are chewing away at the cables. And as these cables get energized during the certain times of the day, you're starting to see sparks, overheat condition, which result in fires. And FM just updated their data guide for rooftop solar system. I think it's FM data sheet 1-15, where they say if the roof structure has certain substrates, certain materials used in the construction of the roof, that they recommend using linear heat in these applications. So we're starting to see a lot of calls for these industrial facilities, these major distribution centers, to look for ways to protect it. We've seen it with CTI, very conducive for an application like this because of its false alarm discrimination. We've seen fiber optic being recommended up here just because of the amount of detection we can carry. And this is a good example of some of those things. FM's data guide 1-15, where they're recommending linear heat detection. Aircraft hangars is another area we're seeing a lot of linear heat detection over the years. In particular, right now, CTI and fiber optic are the two primary detection devices being chosen, simply because it can be programmed and or has that false alarm discrimination. Once you have certain suppressants, foam generators, whatever the type of foam that we're using these days, being able to know when you have a heat event as opposed to a false alarm, CTI and fiber optic are very conducive to an application like this. And we see a lot of road tunnel applications as well. Here in the United States, we're seeing fiber optic being adopted into a number of different facilities, different train companies, road tunnels, things of that nature. And new construction and renovation projects. Within the United States, there's over 6,000 fires that can range in property loss from anywhere from a few $1,000s to hundreds of millions of dollars. And in most of the renovation projects, they already have sprinklers and heat detectors and smoke detectors, but these have all been taken offline. So using CTI in these applications, and this is all part of NFPA 241, you can provide a temporary heat detector within these facilities to be able to monitor for any fire activities that might be happening, as opposed to having 24-hour fire watch. And then, as I always like to tell people, it's a matter of how creative you want to get. There are a lot of different areas where linear heat detection can be used. We've seen it in iconic towers up in Canada. We've seen a large number of covered bridges being renovated over the years for the historical preservation, where they're using linear heat detection in here to deter arsons. Sometimes they'll have a suppression system tied to it that just draws from the water it's traversing. Trestle bridges. This will alert oncoming trains to any compromises that were heat related before the train arrives at that area. And then we're starting to see a lot of data centers where we're seeing the detector being used in interstitial spaces, whether it be in the drop ceiling area above a room, or even in the underfloors as well. And that's about it for today. So the basic choosing of a detector, as we go through it, each detector carries its maximum ambient temperature rating. So the first question we're going to ask is, what's the application? Where is it going? What is the max ambient conditions it's going to be exposed to? That's going to play a lot into what activation temperature you're going to choose. The environment that it's going to be installed, whether it's going to be exposed to chemicals, solvents, oils, will determine whether or not we go with a PVC jacket or our XCR. What's our aversion to false alarms? Is it in an area that's going to be prone to heavy activity and potential mechanical damage? That's where we may recommend either CTI or fiber optic, and then obviously approvals, things of that nature. With that, I'll open it up to any questions that anybody has. I can see one in there.
Yeah, so the one question we've got is, can this be used in an elevator shaft? And
Absolutely.
yeah, and I was going to speak on this just a little bit, just so everybody's aware. ASME, or the American Society of Mechanical Engineers, recently in one of their code books, which covers elevators and escalators, have said that they no longer want serviceable fire alarm devices in the top of elevator shafts. There's a couple of reasons for that. We're not going to get into that, but they've written in a couple of not necessarily exceptions, but ways to handle that situation.
Mm-hmm.
I think probably the silliest is that you can cut an access panel into the top of the elevator shaft. And anybody who knows much about construction knows that that is an extremely costly conversation when we're talking about cutting in access panels in elevator shafts. So the other would be to have non-serviceable devices in the elevator shafts. So we're going to start seeing a lot more specs that are going to be requiring linear heat detection and aspirating smoke detectors in elevator shafts, because we are able to take the serviceable portion of that initiation device and move it into an easily accessible area that's not in the elevator shaft. So linear heat detection is becoming much more prevalent in those elevator shaft applications. I would say that as we move forward, that's probably going to be one of the most prevalent applications that we would see linear heat detection, and it's something that we all deal with quite a bit. So I'll go ahead and kick it over to Gary if you want to speak a little bit more specifically about that, but I did kind of want to lay the code foundation there.
No, absolutely. And as you can probably see on my screen, I just popped up isometric that we put together because we're getting a lot of calls about this. And as you said, because of the changes in the code, they want to minimize or eliminate altogether any need for anybody other than elevator service crews from accessing these shafts. They don't want non-elevator crews in there because of the dangers that are inherent with it. So as we started seeing this start to change, of all the technologies, as you mentioned, linear heat detection and aspirated smoke detection are the two that are most conducive to these environments, simply because we can satisfy code as far as our annual inspection and testing requirements by positioning the end-of-line resistor and all the connection points outside of the elevator shaft. So you still have to make that penetration through the wall. That's a 2-hour firewall. They are going to require you to backfill that with some sort of 2-hour fire stop to make sure that you maintain the rating. But once you have that done, essentially they're going down and around the areas where the hydraulics are most prevalent. So that's usually down in the pit area of the elevators. But also, as the heat rises and things of that nature, positioning up at the top of the elevator shafts as well. So now once you have that installed and in position, so long as you don't have any troubles in your linear heat detection aspect of your panel, your testing and maintenance is done all outside of the shaft. Another thing I always caution on this is that typically in the past, 135-degree spot heat detectors were used, which is fine. We do offer a 135 detector. However, the difference between what a 135 represents with a spot heat detector and what it does with a linear heat detector are vastly different. With the linear heat detector, as I used my analogy earlier with the candle and the melting aspects that we're trying to get from the separators that keep those conductors separate, ambient conditions within these areas are going to be crucial. So 135-degree linear heat detector is going to have a max ambient temperature of 100 degrees Fahrenheit. So what I mean by that is that in the environment that you're going into, you want to make sure that that max temperature within that shaft doesn't exceed 100 degrees, because that's when your polymers are going to start softening and wicking away. It won't automatically go into alarm just because it's at or above that threshold, but it is the process and the area where it's going to start to break down. And if you have vibrations, things of that nature, it's a matter of time when you're going to see those conductors short and react.
Understood. Another question was asked was, do we have a spec to share for the supply cable for the CTI linear heat cable? Gentleman thinks you called it a T-type.
Yes, as a matter of fact, I do. And the T-type feed cable on this, we offer it through our catalog, so it's available through that. But I mean, it's nothing special. So Type T extension grade thermocouple wire is typically readily available through your typical wire and cable distributors. You just have to make sure it's Type T rated, so you have the copper and constantan.
All right, I'm not seeing any other questions.
Okay.
So I'd like to thank everybody for joining. I'd like to especially thank Mr. Paul for coming and hosting this. Very informative. I learned a lot about linear heat detection that obviously I did not know before. So thank you very much for coming out and sharing that.
For more information about Potter products, please visit our website at pottersignal.com. To access additional training resources, check out our online training portal at academy.pottersignal.com. Stay connected with us on social media for the latest updates and news.